Good evening, it is Matt Rogers, and thank you for joining this channel. Thank you also for subscribing. We're going to talk about neutron stars. See, these neutron stars have earned their share of the discoveries from 1967. As a massive star dies, expelling most of its guts across the universe in a supernova explosion, its iron heat, the star's core collapses to create the densest form of observable matter in the universe. When you think about it, a neutron star is basically a giant nucleus. Imagine a little lead pellet with cotton candy around it. That's an atom. All the mass is in the little lead pellet in the middle, and there's a big puffy cloud of electrons around it like cotton candy. In neutron stars, the atoms have all collapsed, the electron clouds have all been sucked in, and the whole thing becomes a single entity of electrons running around side by side with the protons and neutrons in the gas or fluid. Neutron stars are pretty small as far as stellar objects go, although scientists are still working on pinning down their exact diameter. They estimate that they are somewhere between around 12 to 15 miles across, just about the length of Manhattan. Despite that, they have about 1.5 times the mass of our Sun. If a neutron star was any denser, it would collapse into a black hole and disappear. It's the last step on the line. These extreme objects offer very important information, tests, cases that could help physicists to understand the fundamental forces, general relativity, and the early universe. Here are some fascinating facts to get you acquainted. Think about this, folks. In just the first few seconds after a star begins its transformation into a neutron star, the energy leaving is equal to the total amount of light emitting by all the star of the observations in the universe. Ordinary matter contains roughly equal numbers of protons and neutrons, but most of the protons in the neutron star convert to neutrons. Neutron stars are made up of about 95% neutrons. When protons convert to neutrons, they release particles called neutrinos. Neutron stars are made up in supernova explosions, which are giant neutrino factories. A supernova radiates 10 times more than neutrinos than there are indeed particles, protons, neutrons, and electrons in the Sun. It has been speculated that if there was life on a neutron star, it would be two-dimensional. Neutron stars have some of the strongest gravitational magnetic fields in the universe, the gravity strong enough to flatten almost anything on the surface. The magnetic fields of neutron stars can be billion times to billion times that of magnetic field on the surface of the Earth. When you think about this, folks, everything about neutron stars is extreme. It goes to the point of almost being ridiculous. Because they're so dense, neutron stars provide perfect test beds for the strong force, allowing scientists to probe the way through the quirks under different conditions. The intense gravity of neutron stars requires scientists to use general theories of relativity to describe the physical properties of neutron stars. In fact, measurements of neutron stars give us some of the focus of most precise tests in general relativity that we are currently having. Despite their incredible densities, the extreme gravity, neutron stars still manage to maintain a surprising amount of internal structure, housing crust, oceans, and atmospheres. They're a weird mixture of something, the mass of the star, with some of the other properties of a planet. But while we're here on Earth, we're used to having an atmosphere that extends hundreds of miles into the sky, Because a neutron star gravity is so extreme, its atmosphere may stretch up less than a foot. The fastest known spinning neutron star rotates about 700 times each second. Scientists believe that most neutron stars either currently are on or at a point have been, just like pulsars. They spit out beams of radio waves as they rapidly spin. If a pulsar is pointing towards our planet, we see these beams sweeping across the Earth like a lighthouse. Pulsars can spin anywhere from 10 to 100 times per second. If you were standing on the equator of the fastest known pulsar, the rotational velocity would be about 1 in 10 the speed of light. The 1993 Nobel Prize in Physics went to scientists who measured the rate of which a pair of neutron stars orbiting each other were spiraling together due to the emissions of gravitational radiation, the phenomenon predicted by Albert Einstein's general theory of relativity. Scientists from a laser, also from the Gravitational Wave Observatory, the LIGO, announced in 2016 that they had directly dedicated gravitational waves for the first time in the future. It might be possible to use pulsars as giant scale-up versions of the LIGO experiment, trying to detect the small changes in the distance between pulsars and the Earth as the gravitational waves pass by. Folks, this is very important. The wrong kind of neutron star could cause havoc on Earth. Neutron stars can be dangerous because of their strong fields. If a neutron star entered in our solar system, it could cause chaos, throwing off orbits of the planets. And if it got too close enough, even rising tides that could rip apart a planet. But indeed, the most closest neutron star is about 500 light years away, and considering the closest star to Earth is little over 4 light years away, has no bearing on our planet, it's unlikely we'll feel this catastrophic event anytime soon. Probably even more dangerous will be radiation from neutron stars. Magnetic field. Magnetars are neutron stars with magnetic fields 1,000 times stronger than the extremely strong fields of normal pulsars. Sudden rearrangements of these fields can produce flares somewhat like solar flares, but much more powerful. On December the 27th, 2024, scientists observed gamma-ray flares from a magnetar SGR 180620, estimated to be around about 50,000 light years away. In 0.2 seconds, the flare radiated as much energy as the sun, producing up to 300,000 years. The flare saturated many spacecraft detectors and produced detectable disturbances in the Earth's atmosphere. Fortunately, we were not aware of any nearby magnetars powerful enough to cause any damage. Despite the extreme neutron stars, researchers still have ways to study them. There are many things we don't know about neutron stars, including just how many of them that are out there. We also know about 2,000 neutron stars in our galaxy alone, but we expect there'll be billions more. So must neutron stars, even in our own galaxy, are completely unknown. We could also study neutron stars by detecting gravitational waves. LIGO scientists hope to detect gravitational waves produced by these other mergers of 2 neutron stars. Studying those gravitational waves might clue scientists into the properties of extremely dense matter that neutron stars are made of. Studying neutron stars might help us figure out the origin of heavy chemical elements, including gold, platinum, in our universe. There is a possibility that when neutron stars collide, not everything gets swallowed up into the more massive neutron star or a black hole, but instead some fraction that get flung out of the forms of these very heavy objects. Indeed, thank you for watching this very short broadcast about neutron stars. There'll be more videos and short documentaries about other phenomena in the universe and our solar system. Thank you for watching. Kindest regards from Matt Rogers.